Hello students, welcome to Marine Engineering Tutorials. I am Atul Kumar Gupta and back with a new tutorial. Presently we are studying Marine Auxiliary Systems and Deck Machinery. Today we have 19th lecture and the topics are properties of air, perfect gas laws and problems on compression of air. In this tutorial, we will first learn about the properties of air. Then we will learn about the perfect gas laws. Lastly, we will solve some problems on compression of air. Let's discuss these through the following slides. Properties of air. Composition of air. Air is a mixture of gases with 78% nitrogen, 21% oxygen, 0.93% argon, and traces of carbon dioxide, helium, methane, hydrogen, and water vapor. Density of air. Density of air depends on temperature, pressure, and humidity. At standard temperature and pressure, the density of dry air is about 1.225 kilogram per meter cube. Pressure of air. Air exerts pressure due to its weight, which is known as atmospheric pressure. At sea level, standard atmospheric pressure is 101.3 kilopascal or 1 bar. Temperature of air. Air temperature varies depending on altitude, location, and weather conditions. It affects the kinetic energy of air molecules. Heat capacity of air. Specific heat capacities of dry air at constant pressure is 1005 joule per kilogram Kelvin and at constant volume is 718 joule per kilogram Kelvin. Conductivity of air. Air is poor conductor of heat but a good insulator. Perfect gas laws. Which is a perfect gas? A perfect gas has constant specific heat capacities. In fact, there is no perfect gas, but at very low pressure and at very high temperature, these gases behave in nearly the same way as perfect gases. As air is a mixture of these gases, it can be regarded as a perfect gas and follows the perfect gas laws. Boyle's law. Boyle's law states that volume of a given mass of a perfect gas varies inversely as the absolute pressure when temperature is constant. Mathematically, V is inversely proportional to pressure or PV is equal to constant or P1 by P2 is equal to V2 by V1. Charles' law. Charles' law states that if a gas is heated at constant pressure, its volume changes directly as its absolute temperature. Mathematically, volume is directly proportional to temperature at constant pressure, or V1 by T1 is equal to V2 by T2. Combined gas law. Combined gas law is obtained by combining the Boyle's and Charles laws. We get P1 V1 by T1 is equal to P2 V2 by T2, or PV by T is constant, or PV is equal to RT. The magnitude of this constant depends upon the particular gas, and it is denoted by R, where R is called the specific gas constant, whose value for air is 0.29 kilojoule per kg K. For mass of n kg, PV is equal to mRT. Specific gas constant R is obtained by taking the difference of specific heat capacity at constant pressure Cv and specific heat capacity at constant volume Cv. Index of adiabatic compression gamma is the ratio of specific heat at constant pressure to specific heat at constant volume, whose value for air is 1.4. Problem 1. A closed and insulated vessel contains 1 kg of air at 213 degrees Celsius and 1 bar. A second vessel, which is also insulated, has a volume of 0.2 meter cube and contains air at 6 bar and 412 degrees Celsius. Two vessels are then connected by a pipe of negligible volume. Calculate the final pressure of air in the vessel and the final temperature of the vessel. For air, R is equal to 287 kilojoule per kg K. We have the data given for vessel 1, mass M1 is equal to 1 kg, T1 temperature is 213 degrees Celsius or 486 Kelvin. Pressure is 1 bar or 100 kilopascal, and gas constant given for air is 287 joule per kg K. Finding the volume of vessel 1, we can use the equation P1 V1 is equal to M1 RT1, and V1 is equal to M1 into RT1 divided by P1. So we substitute the value mass 1 R 287, T1 286 divided by P1 100. We get the value finally as 1394.8 meter cube. This size of the vessel is very large. For vessel 2, the volume is given as 0.2 meter cube. Pressure is 6 bar, which is equal to 100 kilopascal. Temperature is 412 degrees Celsius, which is 685 Kelvin. Continuing further, finding the mass of air in vessel 2, we can use the equation P2 into V2 is equal to M2 into R T2. From here we can find M2 as P2 into V2 divided by RT2. Substituting the values, we get M2 is equal to 600 into 0.2, R is 287, T2 is 685. So we get the value of M2 as 0.00061 kg. Total mass of air M is equal to M1 in the first vessel and M2 in the second vessel, and we get this value as 1.00061. Total volume of air V is equal to volume of vessel 1 plus volume of vessel 2. So it is coming out to be 1395 meter cube. Determining the final conditions. As the system is insulated, equation as per conservation of energy, we can apply M1 into CV into T1 plus M2 into CV into T2 is equal to M into CV into T, or M1 T1 plus M2 T2 is equal to MT. Substituting the value, we get 1 into 486 plus 0.00061 into 685 is equal to 1.00061 into T. And from here we get the value of T by solving this, and value comes out to be 486.1 Kelvin. PV is equal to MRT, or P is equal to MRT by V. We can find the final pressure. So by substituting the value, we put the value for M as 1.00061, R 287, T is 486.1 as obtained above, and divided by the volume 1395. Finally, we get the answer of final pressure is 100.07 kilopascal. Problem 2. A single stage reciprocating compressor takes 1 meter cube of air per minute at 1.013 bar and 15 degrees Celsius, delivers at 7 bar. Assuming that PV raised to power 1.35 is constant and that clearance is negligible, calculate the indicated power. We have the given data. P1 is equal to 1.013 bar equal to 101.3 kilopascal. P2 7 bar equal to 700 kilopascal. T1 is 15 degrees Celsius equal to 288 Kelvin. Index of compression is 1.35. V1 is equal to 1 meter cube per minute, which can be converted as 0.017 meter cube per second. Work done W can be found out by using the formula N by N minus 1 into P1 into V1 into P2 by P1 raised to power N minus 1 upon N minus 1. Substituting the values, we put the value 1.35 for N, P1 is 101.3, V1 is 0.017, and the index of compression 1.35. The pressures are 700 divided by 101.3. And when we solve this, we get the answer as 4.317 kilowatt. Problem 3. A three-stage single acting reciprocating air compressor has a LP cylinder of 450 millimeter bore and 300 millimeter stroke. The clearance volume of the LP cylinder is 5% of the swept volume. Intake pressure and temperature are 1 bar and 18 degree Celsius respectively, while the delivery pressure is 15 bar. Intermediate pressures are ideal and intercooling is perfect. The compression and expansion index can be taken as 1.3. Estimate A. The intermediate pressures. B. The work done per kg of air. Take R is equal to 0.29 kilojoule per kg K. We have the given data. Dia of the LP cylinder D is equal to 450 millimeter, stroke length 300 millimeter, clearance volume is 5% of the swept volume, intake air pressure P1 is equal to 1 bar, air temperature is 18 degree Celsius. Delivery air pressure P4 is 15 bar. Index of compression and expansion is 1.3 and the value of R is given as 0.29 kilojoule per kg K. We can understand this problem by drawing this curve. We have drawn the 3 stages and we know the pressure, inlet pressure at first stage is 1 bar and the delivery pressure after the third stage is 15 bar. So we will find first intermediate pressures. As compression ratios are in geometric progression, thus we can say that P2 by P1 is equal to P3 by P2 is equal to P4 by P3. P2 square is equal to P1 into P3 or P2 is equal to under root P3 as P1 is 1. Similarly, P3 square is equal to P2 into P4 or P3 square is equal to 15 P2 because the value of P4 is given as 15. P3 square is equal to 15 into under root P3. When we square both sides, we get P3 to the power 4 is equal to 225 P3 or P3 is equal to 6.082 bar. Substituting the value of P3, we get P2 as 2.466 bar. Continuing further, work done per kg of air can be found by the equation W is equal to 3n divided by n minus 1 into P1 into V1 minus V4 in bracket P4 by P1 to the power of n by 1 divided by 3n minus 1. Since we have 3 stages, so the compression process is multiplied by 3 and the index also is divided by 3 as shown in the equation. Swept volume Vs is equal to pi by 4 d square L. Substituting the value, we get 22 by 28 multiplied by 0.45 into 0.45 diameter square into stroke length 0.3, which comes out to be 0.0477 meter cube. Clearance volume Vc is given as 5% of the sweat volume, which comes out to be 0.0023 meter cube. The total volume V1 is equal to Vs plus Vc, which is equal to 0.05 meter cube. We know that V3 is equal to Vc, which is equal to 0.0023. We know that P3 into V3 raised to power n is equal to P4 into V4 raised to power n, or V4 is equal to P3 by P4 raised to power 1 by n into V3. So from here we can find the value, the volume of volume 4, V4. Thus V4 is equal to, substituting the values, 6.082 divided by 15 to the power 1 by 3 into 0.0023. It is equal to 0.405 to the power 0.769 into 0.0023. So V4 we can find out as 0.499 into 0.0023 is equal to 0.0011 meter cube. So substituting the values of n, P1, P4, V1 and V4, we get W is equal to, putting this value 3 into 1.3 divided by 0.3 into 1, that is pressure, 0.05 minus 0.0011 in bracket 15 divided by 1 to the power 1.3 minus 1 divided by 3 into 1.3 and minus 1. Solving this equation, we get the work done per cycle is equal to 0.1468 kilojoule per cycle. Mass of air can be found from the equation P1 into VA is equal to MRP1. VA is actual volume. Actual air intake VA is equal to V1 minus V4. It is equal to 0.05 minus 0.0011, which is equal to 0.0489 meter cube. Now M is equal to P1 VA divided by RT1. Substituting the values, we get the mass of air as 0.000579. Work done per kg of air is equal to 0.1468 divided by 0.000579, comes out to be 253.5 kilojoule, which is the answer. Now we can also use this formula, which is much simpler, but we have used the earlier equation because in the question the cylinder dimensions are also specified. So let's try to find the work done through this equation. So substituting the values and solving it, we get the answer also the same, 253.4, which is nearly the same as the obtained by the other formula. This completes the study of properties of air and perfect gas laws. You can solve any type of air compressor problems by using these examples. This book is written by me and covers all the topics as per the syllabus specified by Indian Maritime University. It clarifies the concepts with simple illustrations. The book also provides answers to all the questions which have appeared in the examination conducted by Indian Maritime University. The book can help the students in preparing for the exam and also to work on ship's auxiliary systems and deck machinery safely. Hope that you have liked the lecture. You can write your feedback in the comment box. If you have liked the tutorial, you may share it with your friends. You must subscribe to the channel for getting notification about the new tutorials. I will be back with a new lecture shortly. Thanks for watching till the end.